Okay, in the previous video what we had looked at was the multicasting scenario, and I had given you an expression which was actually done on my own while teaching in a class. And so, the middle number of switches, the switches which are in the middle stage has to be greater than that particular value. So, that value which I had written was this. Okay. So, in this video what we will be doing is we will be slightly looking into, there are two more kind of efforts which have been done earlier in the past, and I will be just giving another expression which came out from that, and then of course how it compares with whatever we have got. And there is another approach actually of solving it. We will not solve it due to lack of time, okay, but I will give the intuitively the idea behind how that expression or what is the approach, what is the thought process behind computing the number of middle stage switches which are required at least to compute to ensure that for a multicasting system the switch will be strict sense non-blocking. Okay. So, the first one was this actually came by Mason and Jordan. You can actually download the paper. This was in Network, which is a journal's name, and this came in 1972, is quite old actually. Okay. And but it is a very intuitive and very simple result. This even talks about the rearrangeably non-blocking system for multicasting scenarios. In fact, we will be doing a Slepen-Duguid theorem, but that will be for a unicasting case, not for multicasting scenario. Okay. And that is basically the extension of Slepen-Duguid theorem which has been actually used by them. So, but only their unicast part I am discussing here. So, in this case they actually said that there will be a switch, and in fact now onward I am also going to use a very general framework. We call this whole closed network will be identified by N, and there will be such R switches and this dimension. So, N by M switches will be there. So, each of these switches R cross R and they are total M switches. If it is symmetric one, I have N here, and this will be M and this will be R, and a more generic version says that this will be N1, this will be N2. Okay. So, this will only depend only on this particular thing. So, this input and this input has to be same, they will depend on these number of switches. Only thing which can now change is the number of switches which are here and number of switches which are here, R1 and R2. So, in general these switches is being represented by your M, N1, R1 and 2 R2. These 5 parameters are good enough to specify the switch. Okay. So, I am actually going to use the same thing. This is what has been consistently used in the literature. So, but before this I had done almost everything in a different format. So, this is the standard which is followed. So, in this case, so now number of multicast, one of the important things which one has to remember is I should not worry about the same number of ports which are here. I have mentioned it earlier also. So far I am able to reach from an input to this switch, I can do a fan out to from here itself to all these outgoing ports. Okay. So, in worst case scenario, so Mason and Jordan actually computed this using a worst case scenario. In worst case scenario, this input, one input is being connected to all the switches. Okay. So, what can happen is you will have the number of these links which will be occupied will be now n1 into whatever is this number of these switches which are there, n1 r2, those many number will be occupied. Now, if one of those links, in worst case if all these are connected, okay. So, in a scenario there is a one free port in one of the switches and there is a one free port here. Basically there is a port which is already connected in a multicast, but that multicast has to be extended to this. Okay. So, there is one less actually he has taken n1 r1 r2 minus 1 which will be here, and these out of these remaining n2 minus 1 must be connected to some other switches here. So, I need one extra switch here by which I can take this free port and connect to this outgoing port. This is slightly absurd. I also then figured out that this is not the correct version which he did. Okay. So, he actually just uses this plus 1, only problem actually is with me is here, I cannot understand this because if all these n are being connected in a multicast fashion to everybody, that is n1 r2, number of links which will be required, because this one the fan out actually is happening here, there is no fan out in the middle stage. So, that was the assumption which has been made by him. Okay. So, there will be n1 r2 minus 1 switches which will be or links will be occupied from this side, and they will be connecting to all the outgoing switches, and then they will be doing a fan out here. Okay. So, if but why minus 1? Okay, it means minus 1 means only one link has not been occupied, but why? So, that question was not there, it has to be n1 minus 1 and they have been making connection to all of them, R2, only one of the input is available. So, this should have been n1 minus 1 R2 kind of thing, but this is the way they actually Mason and Jordan has done, and he says that my this value m, the number of middle stage switches has to be greater than or equal to this. But this anyway is a flawed thing, but since it was there in the paper, I have given the exact expression here. If I would have computed, I would have done it in a slightly different fashion. In fact, this turns out to be same thing which I told you earlier, except this whole thing now has to be reformatted as per that notation. So, if I reformat this, this will become m is equal to f will become R2, because that is the maximum number of fan out which you can have. Remember, there is no fan out here, there is only one to one connections which are being made in the middle stage switches. So, this is not an efficient system. Ideally, I should actually allow the multicasting to happen here as well as here as well as here. Okay. So, this should be R2 into this, N3 will then turn out to be in this case it will be N2 minus 1 plus, so this one was the input dimension here, so this will be converted to N1. Okay. So, this is the what we had actually, and they are both, if you look at the complexities here it is R2 N2, if it is symmetric case it becomes R n minus 1 plus n. For a symmetric case it will become R n minus 1 plus n. In fact, I can write the expansion R n minus R plus n. So, order is R into n, same is true here. So, this is also of order n and R1, but remember here it is N1 which is being used, here it is N2 which has been used. Okay. This comes only because of the legitimacy conditions of the Paul's matrix. Now, but both of these, when I did the Paul's matrix thing, I have never specified that there is no fan out which is happening at the middle stages. Fan out was only happening at the first one and the third stage. But if the first one, in fact, why we should disallow a fan out here? So, we can get a better bound. So, that is what a professor in Stony Brook, State University of New York actually did. So, this is what is. So, this prof actually has come up with an idea that we should allow the fan outs in the middle stages, and then she actually went through an iterative process. So, I am going to give you an idea how this estimate actually is done. Okay. Let me give the complete genesis on which it is actually based. So, the idea says that the way she actually says that, again, if I build up the first stage, second stage, and we have the third stage. In this case, when it goes, this can actually bifurcate here itself, this can also further bifurcate here. Now, this is what we are now permitting, which was not being considered in the earlier cases. Okay. There was no fan out being considered. So, we knew that was an upper bound, that probably we can get tighter bound than that, actually a better estimate was possible. So, this was an attempt in that direction. So, there is the way we define the multicast, if there is an input. Now, this switch, in fact, these ports does not matter. So far I can reach this switch, I will be able to do a fan out here and reach to all the output ports of this one. So, only worry about these switches actually. So, any connection request I from a port number I will be given by the set of these switches where they want to reach. So, this will be set, for example, if this is A, B, C and D. So, this set will consist of A, B, C, D. So, this is the connection request which will be there. Now, another important thing is that this particular switch can reach to, because there is already some connection being set up. So, those we cannot consider, but there will be certain switches which are available. For example, this switch is available because there is no connection, this switch is available. Okay. From these available switches, I have to find out for each one of them, from these available, it might be connecting here, this might be connecting somewhere here, there are other links which are available in this case. So, already the connections which have been made, we call them destination set. So, destination set for this one, if this is 1, 2, 3, 4, 5, 6. So, destination set for 3 will consist of B and C. Destination set of 4 will consist of something here E and F. So, the way we actually do it, we have to find out this connection request II, and we just look into that to which all ones, or basically if I look at this switch certainly cannot be used for setting up a connection from to BC, because those connections have already been made. So, if BC appears here also, I cannot use this middle stage switch. Okay. Now, if I look at the other one, this cannot be used for setting of connection to E and F. But if I am looking at this pair, let me find out the intersection of these two. So, M3 and M4 intersection, this will be, there is nothing common, so it is phi. So, if I use these two, their intersection is phi. So, whatever is the available ones, so we will actually can use that. this is the intersection among all that. So, if I can find out the x such available nodes, available middle stage switches for this switch, or basically their input links are available. For them I find out their destination sets, their intersection, if the intersection with input request I is phi, that actually means I can actually use this particular combination of x different available switches to set up the multicast tree for this connection request. This shall be possible. So, I need to find out the minimum number of x middle stage switches, so that this condition gets satisfied. So, under this premise, she has computed and she found that it will be possible to set up a connection. So, I am giving the final result which actually came. If my number of middle stage switches is greater than minimum of this is for a symmetric switch. So, symmetric switch means where the number of switches here is R, number of switches here is M, the number of inputs are N, number of outputs are also N. Okay. So, we define that thing by M N R. Okay. So, that is a switch. So, M stands for the number of middle stage ones, R stands for the number of switches here, N stands for the number of ports on the switches actually. Okay. So, the result turns out to be this. So, you have to just iterate over all the possible values of x, which will range from 1 to whatever is the minimum of these two, and for each one of them compute this expression, and the whatever is the minimum value which you will get, that is the m which is required. This is a tighter bound than what we had estimated earlier for a multicasting case in a closed network.